I'm Neal Armstrong, for those that don't know who I am. And I'm going to tell you a little bit about 4.1. Practically the only thing I'm going to talk about are the organic solar cells. And part of the expanding world of flexible electronics, which Denise just set up. The work that I'm going to describe is primarily the interaction between our laboratories and those at Georgia Tech. There is an embryonic effort between us and the University of Washington, which has morphed into another center that I'll have something to say about as well. I'm going to be unlike some of the previous speakers in that I think, virtually no equations and no in-depth scientific concepts. So I apologize for the insult to the intelligence. So just pretty pictures here. These are all DO devices. Those are my fingers. That's the only part of the research that I'm allowed to touch. And I'll tell you a little bit more about that. This is his largest area solar cell to date. This is in the background is a conventional solar cell, and then these are all the little test cells that he's worked with. And there are literally thousands of them. So I went back and took Gene's template seriously, and I'm going to go back and define some very simple vocabulary in this area, which really is relevant for all solar cells, whether they be organic or not. All of these systems, whether on a macroscopic or a nanometer length scale, consist of at least two materials, a donor and an acceptor, both of which may be photoactive and which under illumination will undergo charge separation, typically at this donor-acceptor interface. That charge separation leads to charge movement toward collection electrodes, which generates the photocurrent that we measure. In the dark, in an ideal device, and I might say, by the way, I've never seen anyone that performs like this, they have absolutely no current response until we reach an onset voltage, which is called the forward bias region, and extremely low current in this reverse bias region. Under illumination, we simply transpose that entire current voltage curve down, as shown here, and we generate a photocurrent. And in an ideal device, once we reach this saturation photocurrent, there's no field dependence of the photocurrent whatsoever. It's absolutely flat along here, and no organic solar cell that I know of does exactly that. And I'm going to define for you how we extract power from this device. Typically, when you're using a solar cell, you'll work in this region right here, which is where the maximum power is generated from the device, and we'll define some of the parameters that limit the efficiency of these things. So we obviously want to make the photocurrent as large as possible, and we want to make the photovoltage of these things equally large. So the first thing that limits power conversion is the open circuit photovoltage. This is nothing more than the output potential of the device at zero current, and it's controlled by offsets in frontier orbital energies at that donor-acceptor interface. And tomorrow, when we have our breakout session, I'll have a little bit more to say about that. So this is basically the difference between the HOMO, the transport HOMO of the donor, and the transport LUMO of the acceptor. All right. Now, in fact, we never actually realized that full potential difference there, and that's one of the research areas that we're engaged in. We may get as much as up to around 0.3 volts of that number right there, but in some cases we'll lose maybe 50% of that number. The next parameter is the short circuit photocurrent. This is the maximum current supplied by the device at whatever illumination intensity we're at, where the voltage is zero. This is controlled, it's believed at this point, by the difference between the transport LUMO of the donor and the energy of the transport LUMO of the acceptor. This is an photo-induced electron transfer process. It isn't that simple. Many people would like it to be, including myself. It also involves molecular orientation at the nanometer scale. It involves excited state energetics and lifetimes of those excited states. And I would have to say that at this point that our understanding of what controls that current is extremely primitive. It's also, there's a clear benefit to texturing the donor-acceptor interface as much as possible to maximize that current. Then there's this term called the fill factor, which is the ratio of maximum output power versus the theoretical maximum. And this is controlled by all sorts of bad things, recombination, parasitic device parameters, collection current problem or collection electrode problems, etc. Most of the power loss comes from our inability to control that and to optimize that. And last but not least is the power conversion efficiency. In this case, that's equal to the P max times the fill factor divided by the incident power from the sun. And last but not least, and this is really the killer, the cost per watt must be lower than $1. Okay, way lower than $1, or you will never use this stuff. Okay, so just to summarize, photocurrent, photovoltage, there's VOC. This is the short circuit photocurrent right here. The product of those two, we want to make that as large as possible and as cheaply as possible. That's our competition. Okay, it's perfect on micron to hundreds of micron length scales. It's silicon, all right? It's also the stuff that the semiconductor industry didn't want. It's still too expensive. It has to be relatively thick because silicon is a poor light absorber. Because it has to be thick, that also means it has to be incredibly pure. And as a consequence, the cost is right now hovering around $3 to $4 per watt. You guys continue to consume more energy every year despite the recession than you did the year before. Partly because of the technology being developed in this room, which allows us to use more and more technology, which uses more and more energy. All right? Talk to me tomorrow about how much coal it takes to charge your iPod. I'm actually going to try to do how much coal per tweet. Okay? I'm going to pester you guys. All right, there's what we're trying to capture. I'm going to get through this. Since I'm now a slave to the DOE, I've been seeing a lot of these DOE briefings, but this is the one curve that you want to take home here. This is the cost per watt of conventional PV electricity as a function of its cumulative production. This is back around 1976. This is about where we're at right now. This is the middle of the century. This is where a miracle has to occur, right here. It was actually slated for 2010. You didn't produce that yet, so we've let that slide a little bit. The problem is that this cost curve is obeying a perfectly logarithmic function, but it's not dropping fast enough, okay? Widespread dissemination of solar isn't going to happen unless you get the cost down in this region right here, okay? Yes, I'm ignoring you. Okay. It's okay. All right, so this is what we're about right now, okay? And this is, as Denise said, what she said for organic field effect transistors should apply as well for organic solar cells if we get these things right. They should be a disruptive change in this cost curve. If not, this is going to be nothing more than a boutique industry. Okay, there it is. There it is. There it is. There's where we're at. We need to be up here. We're not down there. We're right around here. Most of these numbers are lies, okay? Okay. See me about that. That's what we want to be. That's what we want to be. Every surface covered with solar cells, yada, yada, yada. This is the OPV lifetime table that we're on, we're now held to. Okay, so the government has said that we will be at 12% by 2020 with less than 2% per 1,000-hour loss in power conversion efficiency. I have no earthly idea how we're going to get there. But I have $15 million to help us get there, all right? And I want to give a shout out to the Science and Technology Center, from which the Center for Interface Science Solar Electric Materials was born. Some of the same players that are here now are part of that center. You can see it's a collaboration between us, UW, Georgia Tech, Princeton, and NREL, and we're hoping to solve some of these problems as the STC moves towards graduation and the CIS-SEM ramps up. And thank you so much for teaching me all about how to do this, including things like the Energy Science Group, which is going to be like our GPAC. And yeah, that's enough.